All right.
We just can't look too closely at the writing on the board in the video.
Math in the looking glass.
Yeah. What if we just turned everything around backwards? Could we still do math?
It's just a convention.
It's just a convention. Left to right is a very ingrained convention.
Yeah.
So.
All right, so we thank you so much for being here again. We welcome David Clark back, and
Hello again.
This time he has a specific problem he's going to share with us.
So I'm a big fan of the chain rule. I think it is just one of the prettiest derivative shortcuts you can have. But I want to do this one, derivative of sine of x. And there's a few reasons I really like this. One is just, it's a kind of composite function you don't necessarily see a whole lot if you're doing practice problems. Like, who composes a function with itself? Well,
yeah.
Actually a lot of people do. But this is but you don't necessarily see it out of context. And the other thing is this is a great practice in just keeping track of what you're doing. And I find students tend to sort of get lost in this type of problem. Like there's two different signs, which one is which? What do I need to do with each of those?
Right.
So
for the same reason that we might not even choose it as an example, because it's hard to keep track of the sentence.
Yeah. But the hard stuff is
challenging
good.
exercise.
Yeah. The hard stuff is good because it makes you actually think carefully about, well, what is it the chain rule says, and which part is which part here.
So do you imagine it all ahead of time? Like, do you picture it?
I think a really important thing, I only picture about one thing at a time. I picture the most basic level I can. And in this case, what I picture is like, okay, sine of x, the thing I notice is it's sine of whatever. I don't even care what it's sine of. It's sine of something that's more complicated than x.
So you're really looking at the structure of it as a function right away.
Exactly. Yep, I'm looking at it as sine of, and I know there's an input, and I know it's something I've got to think about. I have to do something with it. And so, like, if I actually map this out, that's the input to sine of x. I really don't care that it's another sine of x. It could be e to the x, it could be log of x, it could be something I've never heard of. And so I actually ignore it, and I encourage anyone watching this to ignore that also, and just think of it as it's sine of red box. So, yeah. That level of abstraction is really helpful to work with. It can save you from getting your brain tied up in knots when it doesn't need to be.
Yeah, I was surprised. So you proposed this function kind of by typo.
Yes, yes, this is not what I meant to write, but it worked.
And I was surprised. I always want to know how things look. And I knew it was going to be periodic because the thing inside's periodic. So that the sign of something periodic should still be periodic somehow.
Maybe funny looking periodic.
Yeah, but then it really surprised me what it looked like when I graphed it.
Yeah, actually, maybe I shouldn't draw a thing. I think, yeah, anyone who wants to know should graph it and look at it really closely. Zoom in a little bit. So, yeah. Shall we get to it?
Yeah, please.
All right. So I know it's composite. The whole thing is composite, so I've got to do some sort of chain rule. I've already mapped out what the inside is. So I usually don't even label these things, like if you've read the chain rule as f of g of x and its derivative or anything. I actually just think of it as there's an outside and there's an inside. And so I'm going to do one thing at a time. This is another thing when I said I don't look too deep into it. I'm going to do one thing at a time. And I know the chain rule says take the derivative of the outside function. So derivative of this and whatever's on the inside doesn't change. So I'm just saying, how does the outermost function, it's doing something, how does it change? Well, I know how sine changes, it's cosine of whatever was there. And I'm still not even looking at that. It's still the same thing, for that matter. So I'm almost thinking of the red box as it's a variable, it's just a thing, and it's not changing, it's not doing anything yet. But then, I managed to work myself off the edge of the board here. But then the chain rule says, and you got to multiply by how the inside is changing. And I'm always thinking of the derivative as something's changing. And so instead of just jumping into it straight away, like I wrote take the derivative of this, I'm saying find how this whole thing is changing. I found how the outer thing is changing, and now I'm actually just going to write down how so close, how the inner thing is changing. That says sine of x. It's that thing. It's the thing in red again.
So the moral is not that it gets smaller as you go farther out.
Right, I mean, it gets harder and harder to read as you go. Yeah. Yeah, when I was in high school algebra, I loved writing everything on one line. Actually, like I'd write a list of problem numbers ahead of time and then write the work for the problems, no matter how much work there was involved. It started to look like this. I made it fit. Yeah, I've learned since then that maybe isn't the greatest choice.
Yeah, that's interesting. Yeah, I did the same thing. I wrote like microscopically.
Yeah.
And now I'm constantly telling students, big,
yeah.
and don't erase mistakes and all kinds.
Use lots of paper.
Yeah.
Yeah. Don't use paper at all. Just type it. Okay, so I wrote the d by dx sign just as a reminder to take the derivative. I didn't try to do it all at once, because the other thing I always did in high school is I tried to do every single step of a problem all at once and keep it all in my head and remember all of it. And that's what I'd be doing if I took the derivative of this step right away. And
that's interesting. So to me, that feels like a little more kind of algorithmic thinking. Like you're trying to follow steps as opposed to...
And I'm trying to break it down into smaller steps that I can deal with on like an atomic basis, just one thing at a time.
Okay.
Yeah. And so I look at this and say, oh, I got to do that still, but I'm going to write a new line for it. I'm going to attempt to write a new line for it. Okay. Cosine of sine of x, nothing changed there. I'm just doing this last derivative. And there I am. And actually, I like thinking about it in terms of how things change, right? How does this whole weird composite function change? Well, it changes in 2 bits. The outside changes and the inside changes, but sort of the miracle of the chain rule is it says the way they change is just found by multiplying them together. There's no new composite anything in it.
Do you have a way you make sense of the chain rule?
Like why it's true?
Yeah.
Yeah, so here's my best way of thinking about it. If I look at a composite function like this, the red box kind of helps me think of, so there's a sign, and whatever's in the red box is telling sign what to do. And it can just be a variable that I put in, or it can be something else going on. And if I want to know how sign is changing, I've got to know where I am in the sign function. And that's what the red box is telling me, is you're sort of traveling along the sign function, where are you? We're not necessarily just following the graph from left to right. This variable is like a controller, right? So this is, you're going here, then you're coming back over here, and you're going over that. It's like a bee flying around somewhere. You don't have any control over it. It just says, here's where you go around to, and sign follows it. Sign does whatever it says. So I want to know how sign changes. It's cosine, but I've still got to let the variable, the thing, move around the same way. Say whatever was happening at some time over here, the same thing's happening at that time over there, but now I'm looking at how fast is it changing, as opposed to where is it located. But then this says, oh, but your variable's changing too, right? The bee's flying around in some weird way. We have to keep track of how it's changing. And so this part is just saying, you got to multiply by how fast that thing inside the sign is changing too.
Yeah.
So in the end, I think of it as it's just a sign of a thing that's changing.
Almost like it's a change of variable or something.
Yeah, and we're changing it into, I could just call that u, and make it just look like sign of u. I have to deal with u's over here. Yeah.
All right.
So that was cool. Now, you said it was, I proposed the example by typo.
Yeah.
I would like to do something more interesting than this. Yeah, I think this is interesting on its own, but I think we could do more. Like that sine of x, why not just throw another sign on?
Yeah.
So, and you can throw signs on in a bunch of different ways, but I want to attempt to do sine of sine of x. So I say I kind of got how this went. What if I threw another sign on?
Yeah.
Yeah.
Looks like a fire and brimstone sermon.
Yes.
So yeah. So what makes that more interesting to you than the original one? Aside from just sheer complication.
Well, yeah, I look at this and I see a stack of signs, and it's a little more interesting because it's like there's a bunch of different things changing. Like that sign does something, and that sign does something, and that sign does something, and they somehow affect each other. But it's still really similar to what we had up here. Like it follows the same pattern. So I should expect to see something kind of similar go on. Like the result shouldn't be that different. So kind of watching for patterns. Also, I think this is a great exercise in making sure we really know how the chain rule works, because you can get lost in all of the signs, but you don't need to.
Yeah, I love that aspect of kind of pushing. Right, so here you've got decent command of it. If you can do this one, you've got it down.
You got it, you mastered it, yeah. And so there's one thing I see a lot of, which is if you look at this top one, there's pretty much only one thing I can identify as the inside function. But if I look at this one, could be that sign, could be that sign. I mean, there's a bunch of different ways to look at it.
Because you said you think of the chain rule as outside, inside.
Yeah.
So identifying what's the outside and the inside.
So there's more than one answer, right? There's more than one way you could do this. I think the most useful thing to do is to look at the outermost function, the furthest out thing, and just say that's outside, and everything else is inside. So I can look at this and say, all this stuff, no matter how wonky it is, that's just all inside stuff. Interestingly, the inside stuff is the same as what we started with up there.
Oh, that is nice.
It's not accidental, really, right?
Yeah.
But this way, the outside function is something I'm comfortable with. Like, I know what sign does, and so I could have chosen it differently. I could have said just this sign is inside, then I got to have all this sign of sign as the outside. I could do that too, but given the choice, I kind of prefer this as the inside, so that there's a single thing outside.
One of the things I like to do teaching is try to think about what kind of misconceptions might come in, and I can see a student thinking about maybe simplifying this by making it sign cubed.
Oh, okay. Oh, that shorthand. That wonderful and terrible shorthand, yeah.
Right, which would still be a chain rule application.
It would, yeah. That's probably worth sketching down here really quick, because if we had sign cubed like that notation, yeah, I always try to rewrite that. I don't like this notation. I know it's totally standard, but I don't like it.
I also hate it.
We don't ever write anything else like this, right? Yeah. I like to rewrite it.
Oop.
Substitution? All right, thank you. I like writing it this way. Oh, wow, that's great. And that's what the shorthand means, right? You're cubing the whole thing. So,
right.
Yeah, but that's composite too, right? There's an inside and there's an outside going on.
Right.
Or you could just multiply it out.
But a completely different idea than the sign, inside the sign, inside the sign.
Yeah, that's a really important thing. This is really just one sign. It's sign of whatever.
Yeah.
This really is three signs all multiplied together, each doing their own thing. So, yeah.
Okay.
All right.
So sorry if that was a distraction.
No, that's useful. That's really helpful. And then there's sign inverse with little minus. Well, that's even worse. So, okay, let it be gone. All right. Mostly. All right, let's do this one. I'm going to do exactly the same thing I did up here. I'm going to say derivative of the outside with the inside thing, and I'm just going to like close my eyes and not look at the inside thing. Unchanged. Yeah, I guess I'll write it over here to make sure I got space. So I know the derivative of the outside, and I'm not even going to bother writing the inside because I know it doesn't change. I know inside that derivative it doesn't change anymore.
And as a representation, that really gets at what's going on.
Yeah, this is a box. Stuff happens in it. We don't really care what it is right now.
Yeah.
But the chain rule says then I've got to do the derivative of the inside.
The correction.
The correction factor, yeah. So now I know how the outside sign is changing. I got to correct for how the variable inside is changing. So that's derivative of what the heck.
Right.
And it's the same. That red box is that red box is that red box. It's all the same.
I like that. You're really using the structure.
Yeah. This is getting more abstract, right? But it's a good reminder that we're just taking the derivative of whatever that is. So if I do that, I can go, okay, cosine of, and I'll just, this is a skill you learn. I don't know if it's useful for much, but yeah.
If you had the green in, then I'll be impressed.
We'll work on that. All right. Times, and this is also a nice thing. Like I said, I don't look too many steps deep. Now all I have to do is just look at this and go, oh, I've got to take that derivative still. Derivative of the thing in the red box. So derivative of sine of x, and I know how to do that.
Oh,
I did that already, yeah. So I mean, I could do all of this work out again, but I don't need to. I can say, I know what that is. It's going to go right down there. So it's that thing. It's cosine of sine of x.
So it's nice that we've got the work done, but really you're applying the chain rule again, right?
I'm really using the chain rule again.
Because the inside also has an outside and inside.
Yep, and so I've really got to do it again. I just realized I was about to do something that is maybe a little misleading, so I'm gonna mention that brief. I was about to start writing this in red. I was about to start boxing in red.
It's not the same thing anymore.
Yeah, this is not the thing in red anymore. It's the derivative of the thing in red. But yeah, to go from here to there, I could actually be careful and write it out. So I'll put it in. I really did have to do the chain rule and say that's composite. So I got to do the derivative of the outside with the inside the same. And then I got to do the derivative of the inside.
Nice.
Yeah. I love how this shows up again. And I could throw another sign on, right? I could do it again. I'm not going to write it out again.
That's interesting. So could we predict even what the derivative of sine of sine of sine of sine of x?
I bet we could, yeah. It would help even more too if I filled the blank in. I'll fill the blank in at the end here so that we get to see all of it together. Because we can sort of start to see the pattern, right? This one was cosine of sine, and then a cosine. This is cosine of sine, and then a cosine of sine, and a cosine.
Yeah.
So there's all these cosines on the outside edges. So I think if you did enough, you could probably see one more cosine, but you'd have even more sines on the inside. One more cosine.
Yeah.
Yeah.
Fascinating.
Isn't that
All
cool?
right. Yeah.
All right. If you want a challenge with this, I'm going to leave this one down here. There's other functions we can compose like this too, and my favorite of all time is, I'm going to put parentheses so it's clear what I'm doing, e to the e to the e to the x. That's e to the all this, and that's e to the all that. So,
Okay.
yeah.
So it's another nested 3-1 like this, but with exponents.
But with exponents instead of being clearly inside parentheses.
Oh, that's a very good challenge.
Yeah.
We'll do that one for math practice.
There you go. Yeah.
Excellent. Well, so thank you again.
Thanks again.
Yeah, I really appreciate you sharing this.
Yeah, it's a lot of fun. So, all right.
Good
luck.
thinking. Thanks.
Let's start with that one. Whoa. Wait, what's going on here?
Oh,
is it recording what's on the screen so that it's recording it backwards, or is it doing some sort of weird mirroring thing?
that's a good question. 'Cause